Yeah. Thanks a lot for reminding me. Yeah. See, and anyway, the notes will be put up, and this I am recording. And so anyway, sorry
So,
for the delay, and thanks for reminding me. Krishna Hanumantu was pleading a lot for recording, so I sort of just now.
sir,
Yes.
will you also share the slides in Moodle?
Shared the things in Moodle, I am not very sure because I was told that in Moodle they may not store videos. Hmm. So
No, not the videos, but the slides.
No,
like
so the notes and the slides.
the slides,
Notes and the slides, yes.
yeah, the slides I will share once that particular this thing is covered. In the sense, I may not be able to do after each and every lecture, but perhaps once a week at least. Okay. And the notes will be maybe slightly more than the slides. Okay, so anyway, you will see. So is it okay? All right.
Yes, sir. Okay.
Yeah, fine, sir.
We will get back to uh, yeah. Okay. Okay. I want to sort of what is it? Showing everyone. All right. So in the real line, you know that mod x minus y is the distance between 2 points x and y. And also by now you must be familiar that in R2 and Rn, one has appropriate notions of distance. For example, in R2, you can sort of even draw pictures and have a good idea. And you may be recalling that many concepts like continuity, convergence of sequences, all these things depend very much on that idea of distance. So now one want to see how much using just this notion one can proceed. That is, say for example, without using the algebraic structure in the real life. I mean, like not necessarily having the algebraic structure as in the real line. So for example, in the real line and in Rn, etc., you know, you can add and then multiply with scalars and so on. Such kind of operations will not be possible in a metric space unless that particular metric space happens to already have that algebraic structure, like for example in Rn. So isolating this notion of distance turns out to be useful in many subjects. For example, to study certain spaces of functions that you will be seeing in functional analysis and courses like that. And also, I mean, my subject is basically probability theory and stochastic processes. And also in when you want to study these things, certain aspects of the mathematical theory of stochastic process and so on, this turns out to be very useful. And as a matter of fact, more or less, these are even necessary. Okay. So now let's get to the definition of what is meant by a metric space. Some of you might already be familiar with, but still. So the distance is a function. Function meaning, yeah, if you can talk about distance between 2 points in that space. So let's say X is a non-empty set, and therefore it is you know that that function should have 2 variables. So it is taken as a function from X cross S to the real line, and that is called, that one has that name, that function we denote by small d, that's called a metric. And so of course, the distance by distance, we have an intuitive idea that it should always be non-negative. So that is the first requirement, that it should be greater than or equal to 0 for every X and Y in capital X. Then the next requirement, that a point will be at a distance of 0 if and only if that point is, I mean, both the points are the same. So that is again our intuitive notion of distance. But you will see that this may not always hold, okay? There may be some spaces where you need to consider when this is not. I will give you an example. One of the examples which we will be showing later will have that property. And as such, such spaces also happen to be useful, some of such spaces. And in such cases, one might see what one can do, okay? That would be, of course, many of those things may not be in this course. We will talk about it as and when we come to it. Then, of course, the symmetry. The distance between x and y is the same as that between y and x. So there is no intuitive hang up about that. Then one of the crucial things, the triangle inequality holds. So that is, you know that one of property of the triangle which you all must be familiar with, if you have a triangle, the one side will be shorter than the sum of the two other sides. So that's a triangle inequality. And you yourself can draw a picture, right? You don't want me to unshare the thing and see the picture. So I hope this is something which is pretty obvious. And I would also suggest that as you are listening to some of these things, it might be a good idea to have some sheet of paper and draw some of the pictures on your own concerning the plane, that is the R2, where you can more easily draw pictures and see. So for example, the triangle inequality you can see, comprehend or more clearly when you draw a two-dimensional figure, a triangle, for example. I take the vertices to be x, y, and z. So if you have a non-empty set along with this function having these properties, that pair x comma d is called a metric space. Okay. A subspace. So if x is a metric space and S happens to be a non-empty subset, like for example you have the real line and the unit interval. Unit interval is a non-empty set, and you restrict that function. So then in that case, S cross S becomes a subset of x cross x. So you restrict this function d to S cross S, and confined to S cross S, you can easily verify that d from S cross S to the real line also satisfies all requirements of a metric. So therefore, we call this S as a metric simply subspace of x comma d. Of course, it is in this, when you state like this, it is understood that the distance function on S is also same as the x, that is d. Okay. So we come to one of the first, I mean, of course, we have already defined what is meant by a metric space. To operate with that, we may have to have more definitions. So the basic thing is what is called an open ball. So it is something like on the real line, you have an open interval. And for example, in the R2, this will correspond to a sort of disk, the interior of a disk. In higher dimension, but of course, that these things you should keep in mind that it also depends on what metric one chooses. So soon we will see examples where you on R2 and the higher dimensional spaces, Rn, you can have more than one metric. So it also depends on what D you choose. So if you happen to choose in R2 the usual notion of distance, that would be in that case it would be that interior of a disk with radius r around the point x. So the ball with it, so it is called open ball, and that is open ball centered at x, and with the radius r is all those points in the space X which are at a distance strictly less than r. And the strictly less than r sort of corresponds to open. Okay. All right. A related concept is what is meant by an open set. So a subset of the metric space is said to be open if for each point there is an open ball around it which is strictly inside that set. I think if you have any this thing, I will draw a picture and show you. Which means I have to now stop sharing and then go to, can you all see the picture? Okay. If you, since you are all muted, if there is,
Yes, sir.
yeah, if, yeah, since you are
Can
all,
you lift the paper?
huh?
Can you lift
So can you lift the paper a bit?
Is it okay? You can see the picture here. Is it
Yeah.
okay?
Yeah.
I mean, this is the kind of picture which you yourself can draw if you are sitting with a paper and pencil. Okay. So, as a matter of fact, while lecturing in a classroom, such things one may draw easily on a blackboard. And unfortunately, I am still not confident of using whiteboard and things like that. So, you have to sort of bear with me. Okay. So now we'll go back to the screen, sharing screen. Okay. So you keep your thing normally in the audio in muted, but whenever you have to ask something, you can unmute. But if I ask a question like this, if you are silent, I will generally take it as that everything is fine. You don't have to open unmute to comfort me that everything is fine. Okay, that will be the default assumption I should make. Okay. Yeah. So we will have a small lemma. So I sort of dispose of this particular thing at the beginning itself. And this thing says that, first of all, every open ball in a metric space is an open set. I mean, that's perhaps pretty obvious, but still we state it. And secondly, which is more important, arbitrary union of open balls is an open set. And also the converse, any open set is a union of open balls. Again, both are fairly obvious. So, for example, in R and the real line, generally have the open sets basically are open intervals and unions of those things. The in R2, for example, just like the picture I showed, an open set need not always have exactly a circular boundary and things like that. It can have sort of curves. It can even have corners. It doesn't have to be smooth. So such things, and an easy way of sort of intuitively having an idea about the second assertion, basically the way you have been using graph sheets, right? So in your class 10 or perhaps may not be plus 2, even earlier, if you want to sort of calculate the area of a bounded region on from a graph paper, you sort of, from that you count the number of squares in that graph paper, and that will give you a good estimate of the area of the region which is contained within that boundary, the figure you draw. And it depends on the resolution of your graph paper. If it is very finely calibrated, you may have better answer. Okay. So the second statement in this lemma is basically an abstract version of that. Okay, fine. So the proof is pretty simple. So the first assertion concerning the open ball, which is very clear. If you have a paper and pencil, you yourself can draw. You draw an open ball with the radius r around a point x and take a point inside that ball. And basically you have to take a smaller circle of say, radius less. That is this thing. Now you may not be able to see me because the current, the power has failed here. Let's hope that it comes back fast. But then you can see the screen. All right. So this proof is just, so one can show that around y, that ball with the smaller radius that you draw is completely contained in the bigger ball. That's pictorially very, very obvious. And we are just going to write it in mathematical terms. That's it. So you take an arbitrary point in the smaller sphere, smaller ball, and use a triangle inequality to sort of show that that ball has to be contained in the bigger sphere. So that proves that the smaller ball is contained in the bigger one. And here you might notice that the one less than or equal to symbol and above which a question mark, if you come across that thing, I want you to pay some attention to it and clearly understand why that strict inequality is valid. Okay, so and that these are all pretty simple, so I don't have to really stress the thing. All right, the next thing. Suppose the set U in the metric space is the union of an arbitrary collection of open balls. Okay. So that is, it is of this form. U is equal to union over U alpha with alpha varying over an index set I. This I, if what happens if I happens to be empty? Though then that will be union of an empty collection, and that kind of union is generally taken as the empty set. So for example, this gives you this empty set is an open set. And similarly, on the other extreme, if that U alpha is the collection of all possible open balls in the metric space, then clearly that union is going to be the whole space. So the whole space is also an open set. And these two observations, that the empty set and the whole space are open sets, I have not really written it down, and we will see it little later. And there is a reason for that. I will mention that at that time. Okay. Now, suppose now we want to prove this statement. So the two extreme cases we have taken care of. Now that I may be any arbitrary index set, which may be finite number of points. I may have finite number of points, or a countable number of points, or an uncountable number of points. We don't know. So suppose this, the point y belongs to U, then it has to be in one of the U alphas for some alpha. And of course, since all these U alphas are assumed to be open balls, so clearly U alpha should be of the form dxr, for which must have a center x and a radius r, which is strictly positive. So that. And from the proof of the first statement that the open ball is open, you have already seen what I have written there, that there is a smaller ball around that y, which is strictly contained in the bigger ball centered around x. So U is an open set. And of course, the converse is clear from the definition of open set itself. So this completes the proof of the lemma. All right. So I proceed to the next thing. And this is a kind of neighborhood, a convenient concept to have So let U be some subset of X, and that there be a point, X be a point in E. So if you can find an open ball, of course, with positive radius around X, which is contained in E, then E is called a neighborhood. Say here, we don't insist that E should be a open set. Okay. So, for example, in the real line, if you take the, let's say the point, let's say X equal to 1, then the closed interval 0 to 2 can be considered a neighborhood of 1. The open interval 0 to 2 can also be considered as a neighborhood of X. And not only that, hello, please mute your audio, please. And also the set which is open at 0 and closed at 2, and similarly closed at 0 and open at 2 are also neighborhoods of 1. Not only that, that 0 to 2 union just the point singleton 3, that is also can be considered as a neighborhood of X, neighborhood of 1, and so on. So this becomes a kind of a convenient way to say that X is sort of in the interior of that set. I have not yet defined what is meant by interior, but from our intuitive notion of what is interior, so that is something which you can see.
Sir.
Yes.
I have actually a question. You are defining E to be the neighborhood of X.
Yeah.
And then you are telling that in an open set is an open neighborhood of every point in that set. Why are you using the two terminologies different? In the second line, you are using the term neighborhood. In the third line, you are using the term open neighborhood. Is there any distinction?
No, the last line is just to give you an example of a neighborhood. Okay? And here, if you want some examples, I have mentioned now, you can take as an example where E is not an open set, but which is a neighborhood. Is it okay, or you have something more to say?
No, it's okay. Okay, it's fine.
I mean, what the point is that by neighborhood, we don't always mean it need to be open. Okay. So it is just
actually, sir, in some books like Rudin, they define neighborhood as simply by specifying the center and the radius. I mean, neighborhood of a pointer, neighborhood of a point X with radius is simply the open wall.
Is something which there will always be bound to be this thing. There may not be complete agreement on this kind of terminology. Okay, so this may differ from book to book. So this seems to be more convenient, because whenever we say neighborhood, if it is always understood to be an open set, then that can create some minor problems. There is not a major problem. It is just a convenience. Okay, that is why we have not given it as a kind of definition, but more listed as a terminology. Okay.
Okay, sir. Okay.
All right. So, by the way, this kind of a thing, there will be, what you should see is, when we say something throughout our course, one is being consistent with that terminology. Okay. So, if you compare with some other book, there will be certain differences. But on the other hand, regarding definitions like open sets and things like that, there will be no difference. Okay, that's a kind of universally accepted concept, universally meaning among people who are interested in mathematics. All right. Okay, we want to next go to some examples. So one of the examples, the first examples we are going to see is certainly the real line and also R. So basically, I'm recalling the Cauchy-Schwarz inequality, which I am pretty sure that all of you would have seen, and that I am just stating it as a theorem. I mean, this is if you have AI and BI, let's say n real numbers, I mean n and this thing. AI is one set of n real numbers, BI is another set of n real numbers. Then this, the product of AI, BI and summed over this thing. So that is basically if you, the AI can be considered a vector in Rn. Similarly, BI can be considered a vector in Rn. So what we have on the left side is basically the inner product or the dot product between the two vectors A and B and square of that. And that is less than or equal to, so this, that is summation over I, A squared. So that is mod A squared. That it's the length of that vector squared. And similarly for B. So you know that this inequality holds in the language of the inner product between the two vectors in Rn and is less than or equal to the product of the lengths. And only thing is we have expressed in terms of the squares. And incidentally, this is also true when AI and BI are complex numbers. In that case, the only difference that the care you have to take is that on the left side, it should be the product of AI and BI bar. BI bar is the conjugate of BI. And on the right side, you should, the summation AI squared should be taken as the mod AI squared. That is AI bar product and that summed over I. Similarly for BI. Then the thing is true. And I think many of you would have seen the this Cauchy-Schwarz inequality and its proof even with the complex AIs and BIs. So for example, I think it is perhaps proved in Rudin and also maybe proved in Apostles analysis. And even this proof which I am giving, many of you would have seen, it is basically that you take the fix some arbitrary x and take x times a, that vector, and b. So you add these vectors, I'm talking in terms of the language of Rn, and take their length, square of their length. And then you know that that has to be always greater than or equal to 0. So now you put AI equal to as given here, summation AI squared. So that will be, and B equal to this, summation BI squared. And those happen to be the A and B happen to be, capital A and B happen to be the right side of that inequality. And C is basically related to the left side. So you have all, obviously AX squared plus 2CX plus B is greater than or equal to 0. And if A is strictly, A is 0, there is nothing to prove. So the right side is 0, which means that each AX squared is 0. So the vector A has to be 0. And in that case, the left side is also 0. So there is nothing to prove. So if A is strictly bigger than 0, you choose this value X to be what is given there, and you get what you want. That is, the left side of the Cauchy-Schwarz inequality is less than or equal to the right side of that inequality. All right. Okay. Now we start with the examples. Of course, the very first example is the Rn with the Euclidean distance d2. That 2 here signifies that on the right side we are taking xi minus yi squared and sum them over I and taking the square root. So that is the normal or usual notion of length of the vector y minus x or x minus y that you have in R2, for example. So that is the thing. So the 2 here signifies that 2 which is occurring on the right hand side, and also that square root, that is 1 over half. So you can also have dn and things like that, where you have xi minus yi square to the power n, the mod, the absolute difference of xi and yi raised to the power n, sum over n, not k, let us say, since we are using n for the dimension, let's say dk. That can be defined similarly, but then for the proof, Cauchy-Schwarz may not be this thing. You need to go to what's called Minkowski's inequality and things like that. So we will not go into such things at this stage. You may see it in other courses. Okay. So this is the usual notion of distance that you are very familiar with. And I leave it to you to check that D is a metric on Rn. Of course, one has given a hint, and I think you really may not even need that hint to work through the proof. By the way,
Sir, we did that in analysis 2, the
pardon?
Minkowski's inequality. We did that in analysis 2,
Minkowski's inequality.
proving that
Okay.
dp is yeah.
Yeah. Okay. So in that case, you will be under. You might have proved it even for any p greater than 1, right? If you recall,
Yes, we did.
Yes, sir, we did.
Yeah, not necessarily just for positive integers. Any number, real number greater than 1. Yeah. What you
Yes,
say.
any real number.
So absolutely, you are right. And those kind of metrics can be. Now that since you have said that, I may try to include that in the problems. Okay. Okay. So yeah. So this thing, since you are all familiar with these things, showing that this is a metric is not at all difficult. Anyway, I have mentioned it as a hint. And as it is pretty obvious that in the one-dimensional case, the open balls are open intervals. And in two-dimensional case, with a Euclidean metric, the open balls are circular disks. And in 3 dimensions, they are non-hollow spheres, open non-hollow spheres, and so on. And in this, with this metric, Rn with this thing, suppose you have, take n equal to 1, that's the usual notion of distance. Say S be a non-empty set, then that S comma D is a metric subspace of Rd. And here, of course, the distance is this. And you can verify that U is an open set in that smaller metric space, if and only if there is an open set in the bigger space such that that set U is the intersection of that open set in the bigger space V, intersection yes. Actually, this is true not only in R, any general metric space, and I think that also you may find as an assignment problem. But some of these things, the subspace and what is open, etc., you have to exercise some care. So, for example, we take the unit interval in the real line. You can convince yourself that the interval 0, half, which is closed at excuse me, 0 and open at half, is an open set in the smaller space, but it is not open in the bigger space. So when you talk about openness and things like that, some amount of caution is needed when you are talking about such concepts. All right. Then the Rn with another metric, which generally is called D1. So that is just the sum of the lengths of all the vectors. This. So this is some of these things. And the length means that is the difference xi minus yi mod. So this is this metric. This is easy to prove that it's a metric, and it is different from the Euclidean metric. So in this case, you can, why it is different? One of the reasons is mentioned here. For example, in the, when you take n equal to 2, you can check for yourself that the open ball with radius r around a point is the kind of, it is a kind of, it's a rhombus, so diamond shaped. So that's usual, supposed to be the thing of diamond in, at least in playing cards, right? Dice. So that's the open sphere, or it is open ball in this metric is basically an open square with the vertices as I have indicated. You can check for yourself. And one more metric. So, which is, we call it D max. So this is basically you take the coordinate of the points xi and yi and consider the difference mod xi minus yi and take the maximum of these guys. So you can sort of easily verify this matrix D max, or which we have denoted by a rho, is different from either of the earlier two metrics, that is Euclidean metric as well as that metric D1. Okay. So the open ball in this thing, let's say ball with the center at x and the radius r is, basically an open square with length 2r with, as mentioned, with x at the center. So that's, you can easily draw the picture of this open ball in this metric. Okay. And next we come to discrete metric space. This is an extreme case. So let X be a non-empty set. So the distance is given by this very innocent looking function dxy equal to 1 if x is not equal to y, and 0 if it is 0. So if we both are same. So that means any point is at a distance 0 from itself, and any other point which is different, that is at a distance 1. It is very easy to check that this D is a metric and every subset of X is an open set. So this is a kind of an extreme case. Say X can be a finite set, or it can be a countable set, or it can even be an uncountable set. One convenience of this metric space, I would say, I mean, one of the conveniences, if any statement or result, theorem or lemma is mentioned to you about metric spaces, you can check first that it holds it for discrete metric space, so that to convince yourself that perhaps there is no internal contradiction in the terminology involved and so on. Or in some way that might mean that the statement of the theorem has to be sort of carefully written. Okay. As we had said earlier, we said that this concept of metric is useful in dealing with certain spaces of functions. So one such space is what is called C01. So this is the space of all real valued continuous functions on the closed unit interval 0, 1. You might already have come across this space in some other context. In any case, and define the distance between two elements f and g in that space to be, you take the difference between fx and gx, that is modulus of that distance, in on this distance mod fx minus yx is the usual distance on R, because these are real valued continuous functions. So the distance on the range R is being used to define a distance on the other space, C01. So you take mod fx minus gx and take the supremum over all x varying between 0 to 1. So first of all, you need to see that whether this is well defined. You know that any continuous function on the unit interval 0, 1 is bounded. So therefore, you know that f and g are bounded functions. So therefore, that supremum will exist. Therefore, it is well defined. And then showing that this is a metric is pretty simple. And this metric is also called a uniform metric on C01. And in this metric, the open ball, you can draw the graph of f, and above that, let's say the line which is at a distance r from the graph of rather minus r, let's say, below the graph, and another curve which is parallel to the graph of fx and at a distance r above the graph of that, and you have that band. So the open ball with center at f in this space C01 and with radius r, it consists of all those functions whose graph lies entirely within this band. I think that is pretty obvious. You just draw a rough diagram with your paper and pencil. In a similar way, instead of the closed interval 0, 1, if you take a closed interval a to b, also that similar thing can be defined. Only thing is, in that case, that supremum may have to be taken between a and b. Okay. So on the same space C01, we have now another metric, which we will call it as L1 metric. And the reason for L1, you may not be able to tell you at this stage. Perhaps you might see in some other courses. Excuse me. So the base space X is the same, C01. And you also know that any function in C01 is Riemann integrable. Excuse me. Now define this distance rho fg as the integral from 0 to 1 mod fx minus gx. And I leave it to you to check that rho is a metric on C01. So the only thing you have to take care in proving that this is a metric is that rho fg equal to 0 implies f equal to g. So for that, I have given the hint, that is namely mod f minus g is continuous. You observe that. And also mod f minus g is greater than or equal to 0. So now f equal to g, if it is not valid, that means mod fx minus gx is strictly greater than 0. So you can choose an epsilon in between 0 and that point. So and for some x. In continuity, you argue that it has to be strictly positive in an open interval around that x. And that will contradict your assumption that the distance between f and g is 0. So that's another metric on C01. As a matter of fact, later on you will see that C01 will sit as a subspace in a somewhat bigger space. The next example, you take all sequences of real numbers which are between 0 and 1, including of course 0 and 1. So this is the space of all sequences in 0, 1. And you define the metric as, that is now the points in X are, a typical point would be a sequence. So you have to define the distance between two sequences, let's say xk and yk in X. And of course, since the sequence k runs from 1 to infinity, you have to bother about convergence as well. So therefore, one attaches a weight to corresponding to each k. So for example, if we just say that summation over k mod xk minus yk, you will have issues concerning convergence. So to avoid that, so this is one strategy one follows if you have to, in some sense, deal with infinity of indices in some while considering summation and so on. So the distance between these two sequences, xk and yk, is defined as you take mod xk minus yk for a fixed k, and then that distance you divide by 2 to the power k, and then sum over k. So that kind of a strategy, I don't know, you might or might not have come across in other contexts. But anyway, so that is a strategy which is usually followed when you have to deal with a countable number of such things. So then it is easy to show that D is a well-defined metric, though the metric might look strange to you. Showing that this is a well-defined metric is not at all difficult. I don't want to spoil your fun, so you can show that yourself. And this, yes? Did anybody say?
Suppose we have, yes, sir, suppose we have some metric space X, then can we like define some like, can we make some like all Cartesian products of like X with itself as metric space by considering some kind of supremum
for product space you are talking
about? The kind of thing that
do you mean product of metric spaces?
Yeah, specifically the product of like some metric space with itself, like some number of times.
Yeah, see, the thing is, we will see some of those things we will discuss perhaps in the next class or maybe the class after that, but only finite products, okay? With infinite products, one may have to be, more care will be exerted, and some of those things you might see in your topology course. All right. So, and product of two or a finite number of metric spaces is not all that difficult to handle. But here, this metric space, even it can be considered as a product like this, but if I say like this, that looks more complicated. That is x equal to the closed interval 0 to 1 to the power infinity. So initially I was even hesitating whether I should mention that at all, but I couldn't resist the temptation of mentioning that this is one way of representing that. But in this course, we will generally be discussing only finitely many product. Okay. X1 cross X2 cross Xk. Beyond that, we generally will not go. But that the discussion, some of this discussion itself would take care of, yes, simple cases like this. Is it okay? Okay. So if
yes,
I think you at least are temporarily satisfied. Good that the question.
Sir, yeah, another question, just out of curiosity, in place of 1 by 2 power k, can we just put any probability distribution such that any probability distribution pk?
Don't come bring in probability, etc. Okay, there are here these things. That weight you have to put in such a way that say for example here mod xk minus yk, you know that is bounded by 2, right? So therefore you should see that since that is going to be always bounded for each k, the other thing should be basically a convergent series. Okay. So one easy way of handling this is 1 over 2 power 2. You can put, for example, 1 over 2.
Excuse me, sir.
Yes. Yes. Please.
Sir, in this particular example, as you said, we can conclude that all such series will converge by the limit on the bounds of the values of xk and yk. Suppose we were taking sequences on R, like sequences on the set of all real numbers. Is there a similar definition? Like, is there a similar kind of norm
What I
which
meant
uses
that
such a
you have
series?
to be very, very careful, those things, okay? Such things may not be that simple to handle. So,
Okay, sir.
infinite products, you not all questions can be answered in this course. You may have to wait, okay? So, certain things which could can be easily handled in this fashion, I might mention, okay? But this doesn't, this thing may not answer all your queries concerning infinite products. And probably that can be a reason or a motivation for you to study carefully the topology courses, okay? And topology, you might also come across uncountable products, okay? So, when is your topology course? Next semester, is it?
Yes, sir.
Okay. So this course, what we are doing on metric spaces can be considered as a bridge between what you had learned last year in your analysis courses and the topology course. And that is one aspect. Another aspect is it is a kind of prerequisite for courses on other branches of analysis like functional analysis and so on. And functional analysis ideas are also used in many other subjects. All right. I think we are now almost coming to the end of the session, right? Is it close to 11:30? Okay. Let me sort of finish with one example, which is not a metric space. Okay. This is, we denote it by L super 1, superscript 1, 0, 1. So this is, it's a collection of all bounded real valued functions on 0, 1, which are Riemann integrable. So this Y is a different space, okay? It's no continuity. These functions need not be continuous. And you know that there are bounded functions on 0, 1 that are not Riemann integrable. Okay, so Riemann integrability we assume. That is, any element of Y is Riemann integrable. So now define this metric lambda fg equal to, as we had defined earlier for C01, mod fx minus gx. And instead of taking the supremum over this difference, now we integrate. So you can see that with this thing, for any f and g in Y, this lambda fg is well defined. It satisfies all the requirements of a metric. That definition we wrote down, except that this lambda fg equal to 0 implies f is equal to g. That is not satisfied. Of course, one way will be true. If f is equal to f, then of course lambda ff is 0. But f equal to lambda fg equal to 0 implies f equal to g. You cannot conclude. For that, you look at the proof which one had, that hint I had given and so on, carefully. So there we use the continuity argument very crucial, and that would not be valid in this case. So I think I will stop here. Yeah, so that such objects are called pseudo-metric spaces. And there is a way of dealing with that, but you will not be able to deal with this in a very, very satisfactory manner in this course. So we will,
Sir,
yes? Yes?
actually I have a question.
Yes.
So if f equal to g, then lambda ff is 0.
Yeah.
But why the converse is not true? Means if the lambda fg is 0, why f need not be equal to g?
F need not be equal to Z. See, you see the proof of our thing C01 there to prove that we used the argument F and G are continuous very crucially. F minus G was continuous there, no? Here F minus G need not be continuous. Okay, so that will fail. This is
Okay, fine.
it's a fairly complicated questions, and to answer that, the thing is you have to go beyond Riemann integrable functions. Okay, so which means you may have to get a complete answer, you may have to wait for a course in measure theory. All right, Lebesgue integrals and things like that.
Okay, means to construct such functions f and g which are bounded, for which lambda fg is 0, but f not equal to g.
No. See, that is
difficult at this moment.
It is fairly. See, the thing is, you can take f to be a continuous function, and then g can differ from f at, let's say, finitely many points, right? Yeah, simple counterexamples can easily be given.
Yes.
All right. So here you are not bothered about continuity, isn't it? Okay. And I think
Okay, fine.
for today we will stop here. And no, what is it? I have to do to. Wait. I just thought I will. Now you can now see me. So that's it for the day. Okay. And next class will be on Wednesday at the same time, 10:30 to 11:30. So I will try to send you the code and all that. And if any, somebody has asked some questions. You don't bring in more terminology which we have not yet used in the class, okay? So, okay. All right. So, have a safe day and hope everyone is able to attend every time, and wish you all good health and all the best. Okay, see you next time. Bye.
Sir, one question. Who are our TAs?
Yeah, I think I had mentioned it at the beginning of this session. The TAs have not yet been decided because I don't know. See, I was told that Professor Sukendu Mehrotra is in charge of allotment of TAs, and I contacted him, and I am yet to get any. Maybe he's not able to fix them yet. Okay. So I think since this is a
And I also missed the thing about like what procedure for assignment, like how much weightage and all. If you mentioned, I don't.
These things now, these are all troubled times, right? So one has to sort of decide these things, and I think Karandikar was telling me about the final exam has to have a certain amount of weightage. And what are the norms which will be followed this semester? I mean, it will be very nice to decide many things beforehand, but we are going through times where it is very difficult to predict anything about even how things are going to be after a week or after a month. So many decisions will be taken as and when the contingency arises. So some guideline might be there, and I will follow more or less whatever guideline is suggested by, let's say, the people concerned, so that there is no great difference in the way of evaluating between various courses. So these things one has to see. And also, as you know, the TAs in the CMI are generally the third year students, right? They also have coursework. So I don't know how it is all going to pan out. One person from third year student has volunteered. I have no objection to his being TA, but he may not be able to handle the things of 60 plus students all alone. So I think some more TAs may have to be named to me. Once they are named, then as soon as that, I will try to let you know. Okay. Okay. So I think we have almost had a 1 hour, 40 minutes session, not no, 1 hour, 10 minutes. Okay. So, well, any other question or any other clarifications you need?
So weightage distribution of assignments and exams, and some exams or midterm exams. Is there any?
That's why I'm saying all those things. What is the assignments I can send you as soon as I make them, and also once I covers a significant portion, right? And also I should gauge the speed. For example, today had between a blackboard lecture, I think I might not have been able to cover so much. See, several examples I wrote down. I don't think I would have been able to manage, write all those things on the blackboard within an hour and 15 minutes. Perhaps you may or may not agree with that. So I think had it been a normal class hour blackboard lecture, possibly I might have been able to cover only about 2/3 of what was covered today. And also I don't want to go at that.
Sir,
Excuse me, sir.
Yes.
Sir, where will the recording of this lecture, and subsequent lectures be available, sir?
I have to talk to Professor Krishna Hanumantu. He had suggested something, and I have to see that if I can handle that in a satisfactory manner. Okay.
sir, sir,
Yes.
sir.
Yes. Yes. I can hear you.
So regarding the book,
Ah.
yeah, regarding the book, you tell it is introduction to topology and modern analysis. From where can I get the book?
I don't know that George Simmons book, G.F. Simmons, which is a fairly well-known book. So you can see, I don't know that when I bought it long back, that was at that time itself, it was a cheap edition. It was perhaps more than 30 years back. Now I don't know where that book is. You can see the net. Something might be.
Okay. Okay, sir.
Okay, regarding the assignments, can we submit through like after taking the assignments, or do we need to scan?
All those things I will follow the guidelines given, because whatever they suggest, since the assignments have to be graded by the TAs, whatever is, and that of course the TAs may be more tech savvy than I am. So whatever they suggest, I will follow. Okay. And unfortunately, questions concerning assignments and TA at this point of time, except that I will be making periodic assignments, but the mode of submission and the mode of evaluation, etc., that will depend on what is the policy they are going to adopt, looking at various constraints of this semester. Okay. So I'm sorry that I'm not able to answer questions. Any question other than?
Sir, please share the slide.
Huh?
Sir, please share the slides.
The place?
Sir, please share the slides.
Like, see, that's done. Professor Hanumantu was suggesting something. I was not very comfortable with that. Let us see what I can do. But certainly the slides will be put up. I can put up separately, yes. But again, the slides I may not want to put it up just after every lecture, because I may have one particular group of topics one will cover and then put it up all at once. Okay. So since I suppose we'll have to see how it can be managed. If the recording you can see, that should be less of a problem. Okay. So since this mode of thing is new, one has to take, and also one has to see what one can do best. All right. Okay. Anything else?
So, sir, are you going to give us notes for the entire semester or like just for few parts?
I had mentioned it earlier. After a significant portion is done, that PDF files containing this will be uploaded in the Moodle, which will be more or less be similar or slightly more than the what I cover in the slides. Okay. Yeah. Okay. So I think we are now almost, it is 11:44. Those who have another class, it is getting late for you. So let me not detain. And so we will see on Wednesday. Okay. Thank you very much. And see you on Wednesday. So I'm ending the session. Thanks.